Welcome to the High Energy Density Science Center Seminar Series. I'm pleased to have with us today Professor Michael Demkowitz. Michael Demkowitz is an associate professor in materials science and engineering at Texas A&M University. He received his PhD in mechanical engineering from MIT in 2005, working with Ali S. Argan on an NSF fellowship. During 2005 to 2008, Demkowitz was a Director's postdoctoral fellow and technical staff member at Los Alamos National Laboratory. In 2007, he was honored with a Los Alamos Postdoctoral Distinguished Performance Award. He received the TMS Early Career Faculty Award and NSF Career Awards in 2012, the MIT Graduate Materials Council Outstanding Teacher Award in 2014 and 2015, and the Texas A&M University 2019 Presidential Impact Fellow Award. Currently, he serves as the director of the Center for Research Excellence on Dynamically Deformed Solids, an NSA-supported Center of Excellence. His group uses both modeling and experiments to investigate the behavior of metals under extreme environments. Demkowitz is an author of over 100 peer-reviewed publications with more than 3,500 citations on Web of Science and an H-index of 32. I would like to extend a warm welcome to him and to everyone else here. And I look forward to hearing his talk. Thank you.
Well, thank you, Paul, and thank you all for having me over. It's a great honor. Of course, I wish I was there in sunny Livermore with you. The last time I visited, my host took me to a wonderful kind of Italian restaurant at a vineyard. So it's, I think visiting Livermore in person definitely has its perks, and that's, of course, besides the perks of actually seeing all of you in person. So I hope that time does come eventually, sooner rather than later. So today I'll be telling you about the response of solids to irradiation by massive particles. This title continues to evolve in my mind as it becomes clearer to me what I want to talk to you about. So it's already changed once, and as you'll see, the focus of this work is really on a particular aspect of a radiation response, which is the creation of thermal spikes. So that's what the talk is going to be about. I wanted to acknowledge the people who actually did this work. So Richard Baumer, Liang Zhang, and Scott Skurlow were former students of mine who did almost all the work that I'm going to show you today, that came from my group. And I also wanted to acknowledge my sponsors, the Center for Materials that are Radiation and Mechanical Extremes, CMIME, which was a DOE EFRC that I was a part of. It doesn't exist anymore, didn't get continued, but it was a great project to work on. I also wanted to thank the DOE Office of Nuclear Energy and the NEAT Reactor Materials Program, as well as there is a Lawrence Livermore connection here. Part of the work that I'm going to show you came out of the Livermore 5th Institutional and Classified Grand Challenge Computing Allocation. So I wanted to acknowledge that as well. Very briefly, just to tell you a little bit about my group, what I work on generally is materials, metallic materials in extremes. So by extremes, I mean things like metals that are subjected to corrosion, so very corrosive chemical environments, high strain rate deformation, which often takes the materials to high stress as well. I'd like to look at high temperature microstructure evolution, severe plastic deformation. So severe plastic deformation is when you take a metal and you deform it to very, very large strains, hundreds of % strain. And I'm also interested in radiation response. Now, I understand that none of these things actually classifies as high energy. By your standards, having had a look at the topics of previous presentations. However, I think that what I'm going to talk about today, which is radiation response, and in particular the effect of thermal spikes, is probably the closest that my work gets to high energy density. So I'll be talking about radiation effects. Now, of course, there are many reasons to care about radiation effects, technological as well as scientific. So in the context of nuclear energy, for instance, in nuclear fission reactors, energetic particles are generated inside the materials themselves. So one of my favorite examples comes from the CANDU reactor, which is Canada's fission reactor program. They're sort of unique in that They have, actually, let me see if I can change to a laser pointer. There we go. They have a fuel assembly that doesn't sort of sit vertically like the ones here in the US, but sits horizontally, sort of interesting setup. And each one of these, circles that you see here is actually a long tube that contains a single fuel bundle. This is a sort of cutaway view. All these sort of cylinders that you see on the inside are uranium dioxide pellets inside of a zircaloy cladding. And then, these are cooled by steam and or by coolants and water-based coolants in these sort of tubes that you see here. When the uranium-235 decays, you get fission products, you get neutrons with energies on the order of 200 megaelectron volts. So that material is continually self-irradiating. One of the sort of things that I find interesting in this reactor is that if you look at my laser pointer, there's a spring here. That's called a Garter Spring that keeps the annulus spacer away from the pressure tube. It prevents them from getting into contact with each other. This little Garter Spring is made of a nickel-based alloy X750. Not important, the details about it, except that it's nickel-based. It's mostly made of nickel. And nickel, if you subject it to neutron irradiation, thermal neutron irradiation, will undergo a series of transmutations where it goes from the naturally abundant nickel 58 to nickel 59, and then the nickel 59 absorbs one more neutron and decays to iron 56 and emits an alpha particle in the process. The iron recoils at an energy of about 300 kiloelectron volts, and the alpha particle has almost 5 megaelectron volts. And so if you look at the dose that little Garter Spring gets, it's about twice as high as the dose that it would have gotten from the neutrons alone, right? So all of these materials are continually self-irradiating from the inside, right? So they're generating these high energy particles. Another context where this comes up is in the context of magnetic confinement fusion, where particles impinge on a material, but this time not from the material itself, but rather from the plasma. So there's, in magnetic confinement fusion, you've got plasma where, eventually once we have a reactor, deuterium and tritium are being fused and you get a 3.5 megaelectron volt helium particle that comes out. That one loses most of its energy in the plasma. So when it actually gets to the wall, it's closer to a few hundred electron volts. But the neutron, which comes out at 14.1 megaelectron volts, flies right through the plasma and impinges upon all of the sort of, solid components that are facing the plasma, and indeed penetrates quite deeply. And in fact, that's exactly where we intend to get the energy out of our fusion reactors, from those neutrons. So the materials, of course, get damaged in the process. And so that's another way the materials become damaged in technological situations. There are a lot of situations in space where radiation plays a very important role. In our solar system, obviously the strongest source of radiation is the sun. But one of the favorite examples that I use, aside from the sun, is the Jovian magnetosphere. So the magnetosphere of Jupiter. Jupiter is an amazing planet in many ways. One of the amazing things about it is that it spins really fast. It rotates at a rate of once every less than 10 hours. So a day on Jupiter is less than 10 hours long. And of course, Jupiter is a much bigger planet than the Earth. And so the angular velocities on the surface of the planet of Jupiter are immense. This whole planet acts as a kind of dynamo, and it generates this enormous magnetosphere, which accelerates are highly accelerated. So electrons, protons, ions, they're all getting accelerated to several tens of kiloelectron volts. And what that means from our perspective, from the standpoint of exploration, is that it's actually really difficult to envision exploring the Galilean satellites. The moons of Jupiter, like Io or Europa or Ganymede, are all close enough to Jupiter that they get incredible doses of radiation. When we talk about the surface of Europa, we know that Europa is covered with a sheet of solid ice, water-based ice, but the surface is actually, has a high concentration of hydrogen peroxide and other kinds of sort of hydrogen, oxygen, ozone, a lot of ozone, a lot of these kinds of, unusual compounds simply because it's being continuously irradiated by Jupiter and its magnetosphere. So if we ever want to go there or send machines there, we have to take that into account. Okay, so there are plenty of reasons to study radiation. So let me give you a little bit of a primer on the interaction of massive particles with solids. So, by the way, massive particles with mass, so not photons, right? Photon radiation, radiation by gamma particles and things like that is obviously important, very different from radiation with massive particles. So I'm not going to touch it. I'm just going to focus on the massive particles. So let's say that I have a massive particle, and this could be a neutron or an ion or even an electron, and it is impinged upon a solid. It's now flying through the solid at high velocity with its high energy. Okay, so this gray thing here is the solid. And when it's flying through, assuming that it's a charged particle, it's actually losing most of its energy to electronic stopping. So it's interacting with the electrons. The electrons, you can think of them as exerting a kind of viscous drag force on this particle. And, and in the case of metals, this is occurring via excitation of the electrons. In the case of non-metals like maybe silicon or some ceramics, you can actually ionize also, so there can be ionization going on as well. And the particle loses a lot of its energy this way. When its energy is very high, the interactions with the nuclei in the solid, right? So the actual, what we think of as the actual atoms, is fairly rare simply because the cross section at high energy for those interactions is very, very small. So as this particle is losing energy to electronic stopping, eventually it gets down to an energy where the cross section for scattering from nuclei is relatively larger, and now it becomes possible for this particle to bounce off of atoms in the solid. And it displaces atoms in the solid from their original locations. So in this little animation that I put together, I have that particle, which is blue, requesting to annotate the share content. I will approve, but I don't know what that means. So I don't know if somebody's going to annotate this, or I can annotate it, I guess, maybe. Okay, I'll try. I'll see what happens. So this particle right here is the particle that was flying through the material. It's going to bounce off of a nucleus, right? And when it bounces off, the particle flies off in this direction, and then the nucleus that it bounced off of gets some energy and flies off in a different direction. That's now known as the primary knock-on atom, or pKa. That pKa can bounce off of other atoms, right? So you get this whole collision of whole cascade of collisions between the impinging particle and various knock-on particles, so primary, secondary, tertiary knock-on particles. This is called the collision cascade. Okay? Eventually, when the energy of one of these knock-on atoms gets low enough, its mean free path becomes so small that it basically dissipates all of its energy in a very, very short distance, and you get what's known as a thermal spike. Thermal spike is basically just a region of space that momentarily heats up to very, very high temperatures, on the order of multiple thousands of degrees, maybe up to 10,000 degrees, depending on the material and the energy of the particle. But it's very brief, heats up, cools down very quickly, and that thermal spike is actually what generates defects, right? That thermal spike is the thing that generates most of the damage caused by radiation in a solid. That damage occurs in the case of crystals in the form of Frankel pairs, so vacancy interstitial pairs. These open circles that I'm showing you here are vacancies. The squares are interstitials. So vacancy is a missing atom, an atom that should be at a certain lattice site and is missing. And the interstitial is an extra atom that's been squeezed in between other atoms, right? So the thermal spike will generate these Frankel pairs. And if I just think about what happens next, well, these things are just going to diffuse around, right? So they're just going to move around. Occasionally, you'll get a vacancy meeting up with an interstitial and recombining, annihilating. So that goes away. But not all of those vacancy interstitial pairs or Frankel pairs are going to annihilate. Some of them are going to be left over. Those leftover vacancies and interstitials can diffuse around, interact with the microstructure. They are actually the source of radiation damage, right? So all the radiation damage that we study in the case of metallic alloys comes from these leftover vacancy and interstitial pairs. that didn't annihilate, that are left over from this process of creating a particle interacting with a solid. So my talk will focus on the thermal spike phase, where the point defects are actually created. That's where I'm going to actually focus this talk. This process of particles interacting with solids is something that we can now model pretty well, at least parts of it. So for modeling the actual collision cascade itself, the thing that we tend to use is a program called SRIM. So I don't know why this doesn't want to start. There we go. Okay, so SRIM is a program that basically just models binary collisions, right? So it doesn't take into account the these sort of nonlinear interactions between multiple many bodies, more than two bodies. It just thinks of the particle interacting with isolated atoms in the solid, and that turns out to be a perfectly good approximation for studying collision cascades. So this process of the particle bouncing around and losing energy to electronic stopping and creating primary knock-on atoms, all these things are reasonably well studied by this binary collision approximation in SRIM. When it comes to thermal spikes, at this point, the energy dissipation that's going on is so localized that you can't really use the binary collision approximation anymore. So instead, we use molecular dynamics. This is an example of a simulation of a 1.5 kiloelectron volt collision cascade occurring in copper, right? So FCC copper. What I've done in this simulation is I've taken all of the atoms that are actually perfect face-centered cubic atoms, and I've removed them. I've suppressed them just for the sake of visualization. And all I'm showing you here are the high energy atoms that are in the thermal spike itself. And so what you see here is something like a miniature explosion, right? It happens on a length scale of maybe a few nanometers, maybe up to 10 or 20 nanometers, depending on the energy. But it's a fairly localized event. It's an event that involves lots of many-body interactions. Can't use the binary collision approximation for it, so we use molecular dynamics. And then once you've created defects, modeling how those defects interact with each other and with the microstructure, modeling the fate of those defects over long times, that's something that's very challenging. There are multiple approaches to it. I've listed a couple of them here. So rate theory, reaction diffusion equations, phase field modeling, kinetic Monte Carlo, accelerated molecular dynamics, just to give a few examples. This is a very, very active area of research. I would say that the majority of computational research in radiation effects is occurring sort of in this area of looking at defect diffusion. But I'm going to focus my talk, as I said again, on this thermal spike phase, which is pretty well modeled, well described by molecular dynamics. Okay. So with that, let me just tell you a little bit about what we've learned about thermal spikes so far. And what we've learned, by the way, has occurred almost entirely through molecular dynamics. Doing actual time-resolved, spatially resolved experiments on thermal spikes is still out of reach. We can't do experiments on these things. So we've learned basically almost everything we know from molecular dynamics. So suppose that I have my crystalline solid. Here's an impinging particle. The first thing that happens in a thermal spike is that this impinging particle dissipates its energy to surrounding atoms through some many-body collision process. And each of those atoms then gets a certain energy, right? So all the atoms that I've shown here with red arrows have received a kinetic energy that's above a threshold energy known as the displacement threshold. And this threshold energy depends on the material, and it also depends on the crystallographic direction of the material, but generally is on the order of a few tens of electron volts. So let's say 20 to 80 electron volts. So there are going to be a couple of atoms that receive an energy that's above this threshold, and then there's going to be a bunch of other atoms that receive an energy that's below the threshold. Okay, so the atoms that receive the energy above the threshold, they're going to displace. So for example, let's say I look at this atom right here. It's going to displace far enough away from its original location that it's going to leave behind a vacancy, and it's going to become an interstitial. Okay, and this other atom here is also going to leave behind a vacancy and become an interstitial when it displaces. This arrow that I drew here, if you look closely, is actually aligned with a close packed direction in this particular crystal structure, and that's not accidental. So if an atom happens to receive a kinetic energy that's above the threshold, and in addition to that, it happens to be aligned with the closest packed crystallographic direction, which in the case of face-centered cubic materials is a 110 Miller index type direction. In a body-centered cubic material like alpha iron, it would be the 111 direction. Okay, if that happens, then you initiate something that's known as a replacement collision sequence. So this thing is very interesting. Basically, atoms sort of hit each other sequentially, like a series of billiard balls, and leave behind a vacancy, but the interstitial is created at the end of that replacement collision sequence, which can actually be quite far from the vacancy. So this interstitial atom is not the atom that was knocked out of the vacancy site, it's the terminating atom of that replacement collision sequence. Okay, this will become important in just a minute. All right, so what happens with these leftover atoms that have an energy that's below the threshold? Well, 20 electron volts, let's say the threshold is 20 electron volts. If an atom has an energy that's below that, let's say 10 electron volts, from the standpoint of solid state physics, that's still an extremely high energy. That's a much higher energy than what you need to vaporize the material. So what happens is that all those atoms that are left over basically, thermalize. Their velocities very quickly converge to the Maxwell-Boltzmann distribution of velocities. So, that all those atoms that are in the core of the thermal spike very quickly become an equilibrium liquid, right? So they reach the form of an equilibrium liquid at very high temperature, maybe 10,000 degrees or something like that, but it is an equilibrium liquid. And in that liquid core, you get all the regular things that occur in a regular liquid. For example, diffusion, mixing, demixing, all those things can occur in that core, okay? And as a result of that, all the vacancy interstitial pairs, or all the Frenkel pairs that happen to be inside or near that core, recombine, right? So once this liquid core resolidifies, right, it's going to lose energy through conduction very quickly to the surroundings. So it's going to resolidify quite quickly within a few picoseconds. All the vacancy interstitial pairs that were not far enough separated from each other recombine, and the only ones that are left over are the ones that were sufficiently separated from each other, and in most cases, they're just the ones from these replacement collision sequences. So in the end, the people have studied how many of the vacancy interstitial pairs survive this process, and it's really a very small number, on the order of a few percent, maybe even 1% of the vacancy interstitial pairs survive. Okay, so that's what we know about thermal spikes. Now you're all experts. You're all up to speed. What I was thinking that I would do throughout the end of this throughout the rest of the talk is just give you a couple of vignettes about work that I've done in my group on thermal spikes. Okay, so here's vignette number 1: thermal spikes in nickel-3 aluminum. Nickel-3 aluminum is a intermetallic compound. It's a very technologically important intermetallic compound. It's a very common strengthening phase in nickel-based superalloys. So it's an L12 ordered compound. This is a view of the unit cell. If you look at the phase diagram, it's not quite a line compound, so it has some width to it on the phase diagram. But in its lowest energy state, it is ordered. However, if you were to go above the melting point, which is just over 1300 C, if you were to go up here into the liquid phase, those nickel and aluminum atoms take on random locations. So if you very rapidly solidify from the liquid into the nickel-3 aluminum, you get a disordered form of this solid, right? So rapid quenching from the melt causes this well-ordered nickel-3 aluminum to become basically a metastable face-centered cubic solid solution. Anything that's between the perfectly ordered and the perfectly disordered state can be described as a nickel-3 aluminum lattice containing a certain number of anti-site defects. So an anti-site defect is basically a location where you were expecting to have an aluminum atom, but you have a nickel atom instead. Or you were expecting to have a nickel atom, but you have an aluminum atom instead. Okay? So thermal spikes generate, these liquid cores. So inside those liquid cores, the nickel and the aluminum atoms take on random locations. When that liquid core resolidifies, the core of the thermal spike is disordered. And this is something that's been seen in experiments. So on the right-hand side here, you see a TEM micrograph of nickel-3 aluminum that was irradiated with ions. And all these black regions that you see here, all those black dots, are actually the frozen cores of thermal spikes. And you can see them in the TEM because those regions are disordered, whereas the surrounding matrix is ordered. And you can distinguish between the ordered and the disordered matrix in the transmission electron microscope. Okay, so you can actually do transmission electron microscopy that colors those two regions differently, but based on their ordering. So this is a process. This process of thermal spikes in nickel-3 aluminum is something that I studied with one of my former students, Scott Skurlow. Scott studied, did a bunch of thermal spike calculations on nickel-3 aluminum. And one of the things that he noticed is that the thermal spikes, have a variety of different shapes. So sometimes they have these sort of elongated needle-like shapes. Other times they have these, elliptical or almost spherical shapes. And depending on the kinds of shapes they have, they generate different numbers of defects. Okay, so we did a little study on this and figured out why that happens. So to figure it out, what we did is we characterized these thermal spikes. We characterized their shapes using a parameter called compactness. And compactness is basically like a volume to surface ratio. It basically takes the volume of the thermal spike, raises it to the power 2/3, divides it by the surface area of the thermal spike, and we can calculate all of that based on our simulations. There's a little normalizing factor here to make it so that the compactness of a sphere is 1, right? The sphere has the highest ratio of volume to surface area. So the compactness of a sphere is 1. Anything has a higher surface to volume ratio than a sphere has a lower compactness. So for example, a unit cube has a compactness of 0.806, all right? And so for each of these thermal spikes, we could actually compute their compactness values. Now, what does compactness do to a thermal spike? Well, it changes the rate at which it cools. In particular, thermal spikes that are compact, right, that have high compactness values, cool more slowly. They have less surface area per unit volume, so their cooling rate is slower. Conversely, thermal spikes that have a low compactness cool faster. So, if I were to plot the temperature inside a thermal spike, let's say it starts out here, and then over some time it cools to the ambient temperature, T sub A, the time scale, or let's say the decay time of this temperature for a compact thermal spike like a sphere is going to be large. The decay time for a less compact thermal spike, like let's say this cube, is going to be relatively shorter. So we actually measured these decay times for all these thermal spikes, and we plotted the decay time versus the compactness. And indeed, the more compact a thermal spike is, the longer its decay time. So this plot here is showing you simulations that were carried out at a variety of different ambient temperatures, right? So we used ambient temperatures ranging from 100 to 900 Kelvin. This is the 900 Kelvin case. You can see that compactness is high, decay time is large, compactness is low, decay time is lower. And of course, the ambient temperature also influences the decay time. The lower the ambient temperature, the lower the decay time, because the thermal transport is faster. Okay? And what effect does that have on defect production? Well, it turns out that when you plot the number of Frankel pairs versus the compactness, and you can also plot the number of anti-sites versus the compactness, you see opposite trends. The more compact a thermal spike is, the fewer Frankel pairs it has. The more compact the thermal spike is, the more anti-sites it has. And this is really easy to explain based on the decay time argument. Right? So if the decay time for a high compactness thermal spike is large, that means that any Frankel pairs that were generated have more time to recombine. Right? So the higher the compactness, the more Frankel pairs recombine, the fewer are left over. On the other hand, the longer the decay time, the more time the nickel-3 aluminum has to disorder in the liquid phase. So the higher the compactness, the longer the decay time, the more time there is to disorder. So that means you get more anti-sites, right? So you get these sort of interesting opposite trends in the defect formation with respect to the shape of the thermal spike. That's it. That's the punchline for this particular vignette. I'll just mention that the student who worked with me on this, Scott Skurlow, was an undergraduate student. He worked with me on this as a sophomore. And for this work, he received the Octa Student Award. I believe that he is to date the only undergraduate ever to win that award. He did go on to grad school in physics and solid state physics, and I believe is now at AFRL, I want to say. So he did a very good job of this at a very early age. So there's vignette number 1. I'll move on now to vignette number 2. In this one, I'll talk about metal multi-layer nanocomposites. So here is a TEM micrograph of a multi-layer of 2 metals, copper and niobium. These kinds of composite materials have been studied a lot over the past decade or two for a variety of reasons. They have a lot of very interesting properties, but one of the properties that they have is that they're very highly radiation resistant. The reason why they're radiation resistant is because when the layer thicknesses are very small, and by small I mean on the order of nanometers or maybe tens of nanometers, then the area per unit volume of interfaces between the neighboring materials is very high. In other words, there's a very large number of interfaces per unit volume. Those interfaces are sinks for radiation-induced defects, right? So these multi-layer composites are quite radiation resistant because of that. Indeed, this material that I'm showing you here on the left was actually irradiated to a dose of 3 displacements per atom using helium ions. And if I had been looking at just pure copper or pure niobium, that I would have seen a lot of voids forming in just the pure copper and the pure niobium. But because this is not pure copper and pure niobium, this is a composite, okay? The defects that would have been generated by this radiation were almost entirely absorbed and recombined at the interfaces. And so this micrograph that you see here is basically void-free, right? So, and that's just a signature of the radiation resistance of these materials. So these materials are radiation resistant, so that's good. One of the drawbacks is that they are metastable. So the interfaces between the copper and the niobium are very, very sharp, very, very clear, sharp interfaces, not diffuse at all. And the reason why they're so sharp is because copper and niobium are phase-separating metals. They're like water and oil, right? So if you look at the phase diagram, there are no compounds, no intermetallic compounds, negligible mutual solubility. These things do not want to mix, right? So the interfaces between them stay very sharp. On the other hand, what that means is that the lowest energy state, the thermodynamically stable state of this composite is just a block of copper on one side and a block of niobium on the other side with no interface, okay? So the interfaces that are in this composite actually create some excess energy. And if you were to anneal this kind of composite at very high temperature, you would eventually get it to spherodize, right? So all the sort of internal layered microstructure would break down, all the particles would become much coarser, and the interface area per unit volume would go down. And as a result of that, the attractive radiation resistant properties of this material would be lost. Okay, so this thing is unfortunately metastable. It's not thermodynamically stable. On the other hand, it's also not unstable, right? So why is it metastable and not unstable? Well, the reason why it's metastable is because if you were to take a perfect layer, right, just a continuous layer of copper and niobium, those kinds of layers are not subject to morphological instability, such as the Rayleigh-Taylor instability that would plague, let's say, cylindrical shaped features, right? So layers, continuous layers, are actually metastable, right? They don't, if you wanted to pinch off a layer, there is an energy barrier that has to be overcome to do that, right? Nevertheless, we do see occasionally that these layers pinch off. So here's an example of a micrograph of a layer that is pinched off. And this pinch off that you see here is actually the first step in the process of the breakdown of the microstructure. And so the question is, if I have this multilayer under irradiation and it's subjected to these, high energy thermal spikes with extremely high temperatures, can the thermal spikes initiate layer pinch off? Okay, so in other words, can thermal spikes destabilize the microstructure of these materials? So we studied this again using molecular dynamics. Here's an example of a model that we use. This particular model has about 2 million atoms. It's about 30 nanometers on the side. So in this particular picture, the copper atoms are yellow, the niobium atoms are blue. We put in a primary knock-on atom that had 100 kiloelectron volts, and we got this, oddly shaped thermal spike. You already know from the previous presentation that thermal spikes can have odd shapes. Okay, and so we modeled this thermal spike. We allowed it to sort of proceed out to a long time. So all the sort of heat was conducted away from the core of the thermal spike. The material inside re-solidified, and we had a look at what was left over, and what was left over is what you're seeing here on the right. So you see that the layers are actually very highly perturbed. The atoms are displaced. The reason why this happens is because copper and niobium, although they phase separate in the solid state, actually mix in the liquid state, right? So if you were to take a high temperature copper niobium liquid, that's miscible, right? So if you have a thermal spike occurring in this material, there's liquid phase mixing occurring inside that thermal spike. And when the thermal spike cools and resolidifies, all of that sort of mixed copper and niobium atoms get frozen in place. Okay? So the question is, do these frozen atoms actually initiate one of these pinch-off events that destabilizes the microstructure of the material? Well, to answer that question, we had to go to longer times, right? So we had to use one of the methods that I mentioned to you previously for trying to predict the fate of all the defects that were generated by the radiation. In this particular study, we used the phase field method. So in the phase field method, what we did here is we took this structure that was generated by molecular dynamics, we converted it into a continuum field. So basically, we went from this discrete atomic structure to this sort of more continuous model, phase field model that uses a continuum order parameter. We use the Cahn-Hilliard equation to model how this initial state evolves, and that simulation is shown here on the bottom left. So what it shows you is that because of the phase separating nature of the copper and the niobium, these two materials actually demix substantially, in the solid phase over a long period of time. So a lot of this damage that was created by the thermal spike is actually recovered, right? The fact that you have a lot of mixing doesn't mean that all of these layers broke down. However, once in a while, occasionally, like in the case of this layer right here, we do see a pinch-off event. So this, for example, is an example of a pinch-off event. This layer up here survived, but this layer pinched off. So clearly, thermal spikes can actually initiate this morphological instability, causing layers to pinch off. We repeated these simulations for multi-layers of a variety of thickness. So we investigated layer thicknesses of 10 nanometers, layer thicknesses just below 20 nanometers, just above 30 nanometers, and just above 35 nanometers. And for each of them, we did these phase field simulations, and then we counted the number of pinched off layers as a function of layer thickness. And what you can see here is that we see these pinch-offs occurring at the low layer thicknesses, but when the layer thicknesses become higher, we no longer see the pinch-offs, okay? You can also plot this as a kind of survival probability, right? Multilayer survives if there are no pinch-offs. It does not survive if there is a pinch-off. So the survival probability at low layer thicknesses is low. Then as soon as you get to about 20 nanometers layer thicknesses, the survival probability goes up to 100%. Why is that? The reason for that is because we, doing some very simple calculations, we can show that the pinch-off events, when they occur, happen because interdiffusion zones from two neighboring interfaces are beginning to overlap. So if you were to look at a typical thermal spike lifetime and compute the liquid phase interdiffusion distance, it's about a nanometer, okay? So if you have a layer thickness that's a nanometer, 10 angstroms, that means that two interdiffusion zones from neighboring interfaces can overlap. That's how you get the pinch-offs. If you have any layer thickness that's larger than that, you will still get those interdiffusion zones, but they're not going to be big enough to overlap. And then during subsequent solid phase demixing, those layers are just going to return back to their original state. So the conclusion here is that composites with layer thicknesses above 2 nanometers remain metastable under radiation. Good news. Okay? So that was vignette number 2. Now I'm going to move on to vignette number 3. And by the way, I'm not really keeping track of time here, so I'm hoping that Paul or somebody will tell me when I need to wrap up. As all professors, I can talk forever. So
you've got about 9 more minutes left.
How many?
9 minutes.
9 minutes. Okay, so that's definitely going to be enough to get through vignette number 3. And vignette number 3 is all I have. So vignette number 3 deals with metallic glasses. So very, very brief update on metallic glasses. Here I'm plotting for you volume of a solid divided by some reference volume V0 as a function of temperature. Now, you know that if I start with a crystal and start heating it, it's going to expand thermally. There's going to be some thermal expansion, okay, up to the melting point. And then once I get to the melting point, there's going to be a change in volume, and I'm going to get a liquid. And if I continue heating, the liquid is going to expand at some different thermal expansion coefficient. Now, if I were to reverse the process and start with a liquid and very, very slowly cool it, if I cool slowly enough, I'm just going to retrace my steps. So, if I cool very quickly, I can get some undercooling followed by crystallization. But if I do this fast enough, I'm going to get down. If I do this slow enough, I'm going to get down to the melting temperature, retrace my steps, go back to the crystal. That's in the case of slow quenching. If I go to very fast quenching, and by fast I mean very fast, like 10 to the 6th per second or so, I may be able to get the liquid to undergo glass transition. Right? So rather than crystallizing, rather than returning to crystalline form, it simply undergoes this sort of gradual change in volume that interpolates between whatever the thermal expansion coefficient was in the liquid to whatever the thermal expansion is in the solid, through this sort of continuous transition with no discontinuous change in volume. Okay, the material that I have left over is going to have some excess volume in it, called free volume. Okay, this is something that is very difficult to achieve in single element materials. Most single element materials do not undergo this glass transition, except maybe at extremely fast quench rates. So for instance, silicon will become amorphous silicon if you quench it at extremely fast quench rates. And by extremely fast, I mean like 10 to the 10 per second. And that's the only real example of a single element material that I know that will do this. Most of the time when people make these kinds of glassy materials, they'll use a multiple component solid, multiple component mixture, right? So for example, copper zirconium is a 2-component metal which can be made glassy by quenching at very high rates. Okay, and people have figured out how to adjust the compositions and adjust the quench rates to actually make fairly substantial amounts of these amorphous metallic materials, or bulk metallic glasses, if you will. So this is an example of a bulk metallic glass specimen. These are sort of centimeter scale specimens of bulk metallic glass. And on the atomic level, these glassy materials are not crystalline. They're disordered, right? So this is an example of a simulation. Comes from the group of Catherine Flores at Washington University of St. Louis. And as you can see, no long-range crystalline order, right? So no long-range crystalline order, that means no vacancies and no interstitials, right? This is not a crystal, so it doesn't really have point defects in the usual sense. So how does it respond to radiation? That's a topic that I addressed with one of my former students, Richard Baumer. He actually went to Livermore and spent a summer working with Vasily Bulatov. This is where that sort of grand challenge allocation occurred. He studied collision cascades in a model of amorphous copper niobium, 50-50 amorphous copper niobium. This particular model had almost 500 million atoms in it, and it was about 200 nanometers on the side, on the corner. Okay, this is by far the largest atomistic simulation that I've ever done in my group. Okay, so this is a view of what that model looked like. Now, what Richard did is he initiated a primary knock-on atom, a niobium primary knock-on atom, at an energy of 475 kiloelectron volts. And here's what he saw. So here we're coloring atoms by their energy, by their kinetic energy. So you're seeing all the atoms whose kinetic energy is 10 electron volts or above. Actually, 0.5 electron volts or above. But then they're colored on a scale that goes from 0.5 to 10 electron volts. So it starts out like this, and then it continues to propagate out, and you get sort of this full-blown collision cascade developing inside the material. Because all of these, structures were actually recorded, we could then go back and analyze exactly what happened. So this is the flight path of that primary knock-on atom. Coming off of that flight path are a bunch of secondary knock-on atoms. That primary knock-on atom actually dissipated 90% of its energy in collisions that were 1 kiloelectron volt or above. Each one of these little sub collisions that came off of the primary knock-on atom generated thermal spikes. So we got numerous thermal spikes in this model. And then if we look at one of those thermal spikes in detail, we'll see that they're typically about 10 nanometers wide, or 10 nanometers in diameter, if you will. And we can then look in detail exactly what's going on inside each of these thermal spikes. So we carried out what's known as a voxel field analysis. So we subdivided the model into voxels. Inside of, voxels, a three-dimensional pixel, basically. In each one of those voxels, we were able to compute averages of potential energy and density and stress. We were able also to fit the temperature from the Maxwell-Boltzmann distribution. We were able to figure out the plastic strains. We were able to figure out the diffusivities. A lot of information, detailed information coming from these simulations. So one of the first things that we could do is figure out what are the locations where the temperature exceeded the glass transition temperature. So all the red boxes here show you the locations where the glass transition temperature was exceeded. Those are the molten regions. Those are really the liquid regions of the thermal spikes. And then surrounding temperature, right? So in this case, the temperature, rose to 350 Kelvin. So above the initial ambient temperature. So it's heated up, but it hasn't melted. Okay. We can then look into individual thermal spikes and see, for example, how quickly did the temperature change as a function of time. So here's a plot of temperature versus time. The x-axis here is time in picoseconds. From this, we can derive quench rates. We can look at how the density changed. We can look at how the mean square displacement of the atoms changed. So as a result of that, we also know the diffusivity. And we can start to actually see what is the state of the material at the end. Okay, so here is a plot of the density versus the temperature in the thermal spike. So as the temperature is high, the density is low. When the temperature drops, the density becomes higher. Okay. When the temperature is high, the diffusivity is high. When the temperature drops, the diffusivity is low. And I'm just indicating to you here where the glass transition temperature is for this particular material. Now, as I showed you before, a few slides ago, when you very rapidly quench a liquid, you quench it through the glass transition temperature, you're left over with a little bit of excess free volume. Right? So that's something that we could quantify out of these simulations. So what we plot here is the density of the thermal spike core as a function of the quench rate that the thermal spike experienced. Right, so first of all, notice that the quench rates here are enormously high. So on the order of hundreds of kelvins per picosecond. Right, so very, very high quench rates, 10 to the 14 per second type quench rates. As a result, there's a drop in density. Right, so there's a drop in density in the thermal spike core on the order of 1%. Okay, and that's basically because of the rise in free volume of the material due to the rapid quenching. There's also an increase in the potential energy. So you can think of these thermal spikes as rapidly heating the material and then quenching it very quickly through the glass transition temperature, yielding a glass which has a lower density than the internal than the surrounding matrix material. Okay, This is a conclusion that we can use to explain a long-known phenomenon in metallic glasses, namely that if you irradiate them, they tend to swell. And unlike in the case of crystalline metals, the swelling saturates. So this is experimental findings from a paper from 1982, published in Scripta Metallurgica, that shows you the behavior of the density of an iron nickel boron metallic glass. So this is the starting density, relative density 1. After a certain neutron fluence, the density drops by about 1%. Okay, so the glass swells. But as you continue to irradiate, it saturates, right? So it doesn't swell without bound. It just swells up to a certain level and then stops. Well, based on what I've shown you, we can explain this as basically the quenching of a thermal spike, as I'm showing here, generating a low density, more and more thermal spikes that eventually start to overlap. And once they've actually covered the entire material, once the entire volume of the material has been exposed, the entire density of that glass has changed. Okay, this also causes changes in the yield stress of the material, as well as changes in the propensity for shear localization. I'm not going to talk about that here, but basically similar reasoning to the one that we use here for density can be used to explain ductilization of metallic glasses thanks to radiation. Okay, I believe I'm running out of time, so this vignette actually had 2 parts, so I'm going to skip the second part and go directly to my summary. My summary is that thermal spikes play a major role in radiation responsive solids, and based on the work that my group has done, I've shown you a couple of examples of how they influence radiation effects. So their shape, in particular, their compactness, can affect the defect formation rates. Liquid phase interdiffusion in thermal spikes limits the thermal thermal stability of nanocomposite metals. But it's also interesting to see that that's only up to a certain up to a certain critical thickness of the layers. High rate quenching of thermal spikes in amorphous metals reduces the density of those metals. So much is known currently about thermal spikes, but much yet remains to be discovered. I think this is an area of very much ongoing continued research. Very interesting development that is occurring over the last couple of years is that we're beginning to actually use our understanding of thermal spikes to engineer materials that have higher radiation resistance. So, picking out the right thickness of layers in a multi-layer composite is an example of that, and I can provide other examples as well. So I'm going to end this talk with just a very simple plug. Paul mentioned at the beginning during his introduction that I'm the director of a center here at Texas A&M University known as the Center for Research Excellence on Dynamically Deformed Solids. This is a NNSA-sponsored center. NNSA runs a program that funds academic research. It's called the Stewardship Science Academic Alliances, or SSAA. The purpose of SSAA projects, such as my center, CREDS, is twofold. One is to do good research, and the other is to create a pipeline of potential hires for NNSA labs, such as Livermore, as well as Sandia and Los Alamos. So we have on our committee here advisors from all the NNSA labs. From Lawrence Livermore, we have Mukul Kumar, who's on our advisory committee. So if you would like to learn about CREDS and about ways that you can collaborate with my center, please feel free to contact me. You can also get in touch with Mukul. This particular center is concerned with high strain rate mechanical deformation, which was not the topic of my talk, but I wanted to put that plug in here because if we find a good way to collaborate, then this is a very easy way for you to get a graduate student working with you for free. So with that, I wanted to thank you, and I'm happy to take any questions.
Thank you very much for the wonderful talk. I'll invite everybody to unmute so we can give a quick applause, and then I'll read off everybody's questions from the chat. So please also write in any questions you have.
It's never easy to figure out how to do applause in in these meetings. I actually ran a meeting a few weeks ago where I needed to do applause. So there's an applause reel on YouTube that you can run. So I basically just did that instead.
Good idea. So Arthur Tam asks, how does electronic heat conduction affect the cooling of the thermal spike, especially in regard to compactness?
Yeah, so absolutely, the molecular dynamics simulations that I've been showing you do not take into account the electronic contribution to thermal conductivity. And I would say that that is probably the largest source of uncertainty in those calculations. So with electronic conductivity, I expect that the thermal spikes would cool faster. However, the sort of characteristic time scale for electron-phonon coupling in a lot of these metals, is on the order of picoseconds, right? So which is the typical lifetime of a thermal spike anyway, right? So the contribution of the electronic component of thermal conductivity to cooling of the spike competes with the time scale for the electron-phonon coupling, right? So the effect is not as large as you would think, based on the contribution of electrons to thermal conductivity. So for example, in copper, thermal conductivity is like 400 watts per Kelvin meter squared, right? So that's with electrons. Without electrons, it's more like 10, right? So 2 orders, well, not quite, maybe let's say an order of magnitude difference, okay? The thermal conductivities differ by a lot. But because there's this sort of time scale for the coupling between the electrons and the phonons, the impact that has on the thermal spike is not as large as you would think based on the disparity in the thermal conductivity. In any case, it is definitely a source of uncertainty.
So he also asks, the results for pKa simulations in molecular dynamics rely heavily on potentials. I wonder how much would the mixing be affected by the quality of the potential, especially with strongly immiscible systems like copper niobium mixture, where the heat of mixing is very large?
Yeah, so you're absolutely right. The potentials are, determine how accurate your simulation is. And as a rule, I would say if you were to take any material that, off the shelf, just, think of any favorite material that you have. Maybe it's a high entropy alloy, maybe it's a perovskite, maybe it's, I don't know, polymer or something. Almost any material that you're going to take off the shelf, we have no good potentials for. However, we have some materials for which we have very good potentials, okay? And the ones that I showed you today, the molecular dynamics simulations that I showed you today, were done entirely on those materials for which we know we have very good potentials. And by very good, I mean not just good in the solid phase, but also good in the liquid phase. So for the case of copper niobium, I actually had a PhD student who was studying the liquid phase properties of copper niobium potentials and then modifying them to reproduce those liquid phase properties. And the reason why we wanted to do that is precisely so that we could have accurate descriptions of thermal spikes. So, with these classical potential simulations, if you put garbage in, you get garbage out. But if you put good things in, not garbage, then you get, I think, reasonable things out. And and one of the ways that we can actually verify that is because we can calculate rates of radiation-induced mixing from our simulations. And radiation-induced mixing rates have been measured experimentally. We can compare our calculated radiation-induced mixing rates to the experimentally measured ones, and they match up basically perfectly. I mean, to within the uncertainty of the calculation and the experiment, they're the same. So we can actually, we have high confidence in those cases. I would not have high confidence in in cases where the liquid phase properties of the potential are not known.
So we also have a question from Lauren Benedict, who asks, in your vignette number 2, did you perform detailed interfacial free energy calculations with the molecular dynamics to obtain the interfacial free energies that you then used to parameterize the phase field model? Or did you grab the interfacial free energies from somewhere else? Thanks.
Well, we did not calculate the free energies. We calculated enthalpies. So we calculated interface enthalpies, and we used those to parameterize the phase field model. Unfortunately, for the kinds of interfaces that we encounter in those composites, I do not know of a good way of calculating their free energies. And trust me, I've looked, I've tried. There just aren't very good ways of calculating the free energies of those kinds of heterophase interfaces. Now, people have used molecular dynamics and various other atomistic methods to calculate free energies of fully coherent interfaces, ones that match, have atom-to-atom matching on both sides. Those are like very similar in structure to perfect crystals, really, which is why you can calculate their free energies. But with non-coherent interfaces like the kinds we encounter in these composites, I just don't have a good way of calculating them. So we basically just assume that the enthalpy is a good stand-in for the free energy, and we use that.
From Charlie Lasnier, in vignette number 3, cooling is not exponential. Why?
Exponential in what?
I think he means the temperature.
Exponential in temperature? Right. So the question is, so the idea is, if you were to start out with, if I understand the question correctly, if you were to think of a sphere with a different temperature from the surrounding, and you then calculate the temperature in that sphere as a function of time, the analytical solution would give rise to an exponential decrease in the temperatures. Is that correct? So basically, the expectation from an analytical solution would be an exponential drop in temperature. Am I interpreting that question correctly?
Yes.
Yeah. Okay. So I don't want to. I hesitate to shotgun this question. I guess the short answer is I don't know. But the somewhat longer answer would be that we've made a lot of approximations when we characterize these thermal spikes. So for one thing, the thermal spikes do not have a uniform internal temperature, right? So their temperature when they're generated is initially non-uniform. The second thing is that these thermal spikes, there are actually many thermal spikes that are close together, right? So we see in this simulation, for instance, thermal spikes that were initially separated, cooling, but then the region in between those thermal spikes is such a small volume of material that it actually heats and it melts, right? So two initially disjoint thermal spikes, are individually cooling, but are actually melting the material in between them. So eventually they merge into one thermal spike, and then that thermal spike cools. So you get these sort of complex interactions with neighboring thermal spikes, which also influence the temperature field. So I would guess that that the reasons are probably down to simplifications like that. The fact that we've ignored sort of complexities of that type in the characterization. That would be my guess. But the short answer is, I'm not 100% sure. That said, how would you expect the, let's see, let's bring back the temperature as a function of time. Yeah, that doesn't look really exponential at all. It looks much more linear than exponential. I agree.
There's another question from Arthur Tim. Is the effect of electronic stopping an electron-phonon interaction in metallic glasses not significant?
Well, electronic stopping is definitely significant. As with crystal and metals, it's especially significant at higher energies, right? So, electronic stopping is actually present at all. I should be more precise about this. It contributes to energy loss by the particle or by pKa's at all energies, at all kinetic energies. It's just that when the energy of the pKa becomes small enough, then scattering from nuclei is also significant. right? So at low energies, you get both electronic stopping and nuclear stopping. For the kinds of energies that we modeled here, so on the order of a few hundred kiloelectron volts, you can calculate fairly easily that that electronic stopping is expected to dissipate on the order of 20% of the pKa energy. So, you know, if you think of, so we're basically, you know, if you think of the 475 kiloelectron volts that this pKa had in this atomistic simulation as being, dissipated entirely through nuclear stopping, then we're basically ignoring, you know, on the order of, you know, an additional 125 or so kiloelectron volts, which would have been there and dissipated by electronic stopping. So that's the approximation that we're making. We're ignoring that 125 kiloelectron volts that would have been dissipated by electronic stopping. Now, how quickly would that couple back to the lattice in a metallic glass? I don't know. Electron-phonon interactions in metallic glasses, if memory serves, you know, and please don't quote me on this, but if memory serves, it is somewhat less efficient than in the case of crystalline metals. So I would expect that coupling to be slower. However, those things would eventually couple back. Of course, before they couple back, they would have also a tendency to conduct away, right, through the electrons. And so I guess the question is, what region of what volume of the material would actually see any energy coupling back from the electrons? I don't know the answer off the top of my head. Okay, but hopefully some of this sort of you know, stream of conscious rumination gave at least a little bit of insight.
Okay, got a question from Fei Zhao. Does the parameter of the thickness of the diffuse interface influence the conclusion in the second example?
Not to the extent that we were able to model. Okay, so we actually did try. We did modify the interface thickness a little bit by like a factor of 2. We didn't, you know, obviously if we make the interface thickness comparable to the layer thickness, then the model becomes unrealistic because it is no longer able to represent the fact that the multilayer is stable without radiation, right? So if we had a phase field model where the interface thickness is comparable to the layer thickness, then those layers would automatically interact with each other in the phase field model, and that would be unphysical. So we modified the interface thickness to within about a factor of 2, and that did not influence our conclusions, our qualitative conclusions, which is that you know, beyond a layer thickness of about 2 nanometers, the pinch-off events do not occur. Now, our interpretation of that is that in the cases where pinch-off does not occur, the reason is not related to the parameters of the phase field model. It's really not related even to the solid phase demixing process. It's more related to the fact that the interdiffusion zones in the thermal spike never have a chance to overlap, right? So in the example that I gave here, the simulations that I showed you here, right? So this thing right here, the thickness of the layers is small enough that the interdiffusion zones from neighboring interfaces are overlapping, right? So you get basically substantial interaction between neighboring layers of copper, neighboring layers of niobium. If the layer thickness is larger, then that overlap doesn't occur, and you basically just get, you know, a little bit of roughening of the interfaces and nothing else, and that recovers to the flat interface after some thermal annealing. You know, and in the phase field model, that's not really sensitive to the thickness of the interface, so long as you're only changing it by, you know, on the order of a factor of 2.
Okay, so we'll have one more question from Anthony Yoshimura. Have you considered the possibility that electronic excitation induced either by the initial collision or the resulting ionic motion can reduce the displacement threshold of the affected atom?
Interesting question. I have not considered it, but it seems like a plausible suggestion. Yeah, I really don't know. It may be. It very much may be. So this is an example of something that I think is a topic definitely of interest within the community. In fact, until recently, I think right now might be the time when an EFRC at Oak Ridge called EDDI might be winding down. But basically, there was this EFRC there that was really devoted to studying just those things, right? So they were interested in those initial stages of radiation damage creation and thermal spikes, and they were interested in things like the effect of magnetic moments and electronic excitations, and presence of elements with different numbers of electrons and so forth. So they were looking into a lot of those effects. I don't know if they looked into that effect specifically. But this is basically just a way of saying that those kinds of questions are very much of interest, and I think that they're only now becoming investigated by the community. Now, one reason why they really haven't been investigated before, or I would say two reasons why they haven't been investigated before, is one, as I mentioned, it's very, very difficult to do experiments at this time scale and this length scale. So I'm not aware of any experiments that have actually resolved these kinds of thermal spikes, at the time and length scale at which they're occurring. And frankly, I don't know if it's even possible. Therefore, most of these investigations have occurred using simulations. And so far, we really haven't had the first principles simulations codes, capabilities, that would allow us to simulate a model that is large enough, right? So on the order of several tens of nanometers, and yet have sufficient physics fidelity, right? So the ability to represent things like excitations of electrons, to go after those kinds of questions. That might be changing just now, right? So just now we might actually be getting some of those codes that will allow us to do large-scale simulations with an accurate representation of electronic excitations to be able to start to investigate those kinds of questions. But yeah, very exciting, interesting question, and time.
Well, thank you very much for your talk. It was very good. And I invite everybody one more time. Let's see if we can get a better applause going. You unmute yourselves right now.